In this video, we're going to look at derivatives and the shape of the graph. We're going to explain how the sign of the first derivative affects the shape of the function of the graph. We're going to state the first derivative test for critical points. We're going to use concavity and inflection points to explain how the sign of the second derivative affects the shape of the function's graph. We're going to explain the concavity test for a function over an open interval. We're going to explain the relationship between a function and its first and second derivatives. We're going to state the second derivative test for local extrema. So let's first start out with the definition of increasing and decreasing. This is similar to the definition that you would have learned in your pre-calculus class. Suppose f is a function and it's defined on some interval I. We say that f is increasing on the interval I if for every output for f of x sub 2 is greater than the output for f of x sub 1, where x sub 1 and x sub 2 are in the interval, and x sub 2 is greater than x sub 1. We say the function f is decreasing on the interval I if for the outputs for f of x sub 2 is less than the outputs of f of x sub 1, whenever x sub 1 and x sub 2 are in the interval I, and x sub 2 is on the right-hand side or larger than x sub 1. Here is what we are seeing graphically, what this definition is. X sub 2 is always on the right of x sub 1, and the output for x sub 2 is larger than the output of x sub 1, which means we are increasing, and the same as for decreasing. To determine the exact intervals in which we are increasing and decreasing, we can look at derivatives. We know that a positive derivative means that the slope of the tangents in that interval is increasing or positive, which means a graph must be increasing. The f of x graph, not the derivative graph. We've talked about that, and we'll talk more about the derivative graph. The same thing, when the slope of the tangent lines are negative, we know that those tangent lines are decreasing from left to right, which means the original function must be decreasing from left to right. So that brings us to our first theorem, the test for intervals of increasing and decreasing. Suppose f is a continuous function on I and differentiable on every interior point on I. That means that we don't have to worry about the endpoints. Then f prime of x is greater than 0, then all the interior points of I, then f is increasing on I. If the derivative is less than 0 on all the interior points on the interval I, then f is decreasing on that interval. We're going to sketch a function that is continuous on its domain with the following conditions. So for the first one, we have the derivative is greater than 0 on negative infinity to 0, 4 to 6, and 6 to infinity. So let's just put an xy axis here. Here's y, here's x. And from negative infinity to 0, so something's happening at 0, from 4 to 6, so between 4 and 6. Now, of course, this is not drawn to scale. We know its derivative is greater than 0 from negative infinity to 0. So that means we are increasing. So we have this increasing function, and then it does something like this. Between 0 and 4, it is not increasing, so it must be decreasing, or it could be constant. From 4 to 6, we are increasing. But at 6, notice that it is not inclusive. That means we must have like a horizontal slide or something at 6, and then we continue on up. And so here's a graph of the function that satisfies the derivative is greater than 0. On the left side of 0, from negative infinity to 0, I am increasing. At 0 to 4, I am decreasing. And notice that 0 is non-inclusive, so that must mean I probably have a turning point, or maybe I have a horizontal slide, or maybe I have a vertical slide, or maybe I have a vertical tangent, or maybe I have a constant between 0 and 6, or 0 and 4. But notice that 6 to 6 is not inclusive, it's not increasing, so that means I must have a horizontal slide right at that moment, right at x is equal to 6. Now this is just an example, it is not the only example, but it is just an example. Let's take a look at our second example, which is f prime of 0 is less, f prime of x is less than 0 on the interval from 0 to 4. So once again, I have y and x, and I know between 0 and 4, so between 0 and 4, here's 4 not drawn to scale, that we are decreasing. I know nothing else between 0 and 4, so maybe between negative infinity to 0 I'm increasing, so my slope of my tangents are positive. And say from 0 to 4 my slopes of my tangents are negative, and then at 4 maybe I'm going back up increasing. So here's an example of a graph that satisfies the first derivative is less than 0 on the interval between 0 and 4. Let's take a look at the next example. We know that f prime of 0 is undefined. Well, that tells me a couple of things. Either f of 0 is undefined, so this is what it tells me. These are the choices. We could say f of 0 is undefined. We could say f of 0 has a corner. So in other words, like an absolute value. We could say that f of 0 has a horizontal tangent. But because of the fact that this is a continuous function, we can eliminate that it's undefined. So if it's not undefined, that means it has a corner or it has a horizontal tangent. So the easiest one to identify where f prime of 0 is undefined, here's y and here's x, would be the cube root. Because we know if we have the cube root that we have a horizontal tangent. If we were to zoom in right here at 0, we would have a horizontal tangent. It is defined, it doesn't have a corner, and so that would be a graph that would satisfy that. Now, the next example, we have f prime of 4 is equal to f prime of 6 was equal to 0. Now, we know when this happens, that means that we have a turning point. Or in other words, I'm going to have a max or min. This means I could have a max or min. It also means I could have, if it's not a turning point, I could have a vertical slide, or excuse me, a horizontal slide. But what I do know is at 4 and 6, I have the tangent is equal to 0. Or the slope, or the tangent of the slope of the tangent is 0, I should say. So at 4 and 6, so here's 4, here's 6. So let's make these a max and a min, and here's a graph. At 4, I have a turning point, and at 6, I have a turning point. Excuse me. So we know that those are the locations in which I either have turning points. I could have made those a horizontal slide, like a cubic type shape at those points. So for this example, or for this graph, we can look at what it means to be undefined. The derivatives are undefined when our slopes are 0, when our slopes are positive. Notice the derivative is greater than 0, so we're increasing. The derivative is undefined, so I have a corner. The derivative is less than 0, so I am decreasing. The derivative is equal to 0, so I have a turning point. Again, I have increasing. My derivative is greater than 0, so I'm increasing. Here's a location in which I have a derivative is equal to 0, but it's not a turning point, it's a horizontal slide. And again, my derivative is increasing. Right up here, we have a derivative that is equal to 0 again. And then here I'm going downhill, so my derivative is, my derivative should be less than 0 right there. So my derivative should be less than 0, not greater than 0, so we are decreasing. So for this, what they want us to do is find the intervals of increasing and decreasing. So the first thing I'm going to do is find its derivative. So I'm going to find the derivative of the cosine. So f prime of x is equal to 2 cosine x negative sine of x. Now I'm going to find my critical points. So I have negative 2, the cosine of x, the sine of x is equal to 0. So that tells me that I can ignore the 2 because if I divided both sides by 2, I just have cosine and sine. That tells me that either cosine of x is equal to 0 or the sine of x is equal to 0 or both of them. Well, in the interval between negative pi and pi, the location in which cosine of x is equal to 0 is when x is equal to pi over 2 and when x is equal to negative pi over 2. The location in which sine is equal to 0 from negative pi to pi is when x is equal to negative pi, 0, and pi. Now, I'm not going to worry about the endpoints, so I won't worry about those. So then what I'm going to do is I'm going to make a sign chart, like what you learned in your pre-calculus 1 class. So I'm going to have negative 2. I'm going to have cosine of x. I'm going to have sine of x. Now, why did I ignore the negative 2 before when I was solving, and why am I putting it here? Well, because negative 2 is a part of the factor, right? So negative 2 cosine x sine x. But when I went to solve for the x, if I divide everything by negative 2, it's not going to affect my cosine of x equals 0 and my sine of x is equal to 0. So now I'm going to break up this into intervals. So my first interval is from negative pi to negative pi halves. So in other words, my breaking point is when x is equal to negative pi halves. I'm going to choose something in that interval. So I'm going to choose, let me choose x is equal to negative 2 pi over 3. Now, negative 2 is negative. Cosine of negative 2 pi over 3 is negative, and sine of negative 2 pi over 3 is negative. Triple negatives make this negative, so that tells me that I am decreasing in the interval between negative, well, we know that's when it's equal to 0, so it's decreasing in the interval between negative pi to negative pi halves. So the fact that negative pi and pi were locations of when my derivative was equal to 0, that means that they are critical points, which is likely a turning point for this graph. My next interval is going to be from negative pi halves to 0. So in other words, when x is equal to 0. So I'm going to choose a value, so I'm going to use negative pi thirds, and this is going to be negative. Cosine of negative pi thirds is positive. Sine is negative, so this is positive. So this tells me I am increasing on the interval between negative pi halves and 0. Now, the next interval I'm going to look at is from 0 to pi halves. Now, I really should be using, right here, I should be using open brackets because I'm not worried about the endpoints. So I'm going to choose something in this interval. So I'm going to choose pi thirds for no other reason than that's a nice value. I could have used pi over 4 over all of these, negative pi over 4, negative 3 pi over 4, but pi thirds is nice. So the negative, of course, is still negative, and this will be positive, and this will be positive. This interval is negative, so that means we are decreasing between 0 and pi over 2. Expand my chart. I didn't give myself enough room. So then my last point of interest is when x is equal to pi over 2. And the interval I'm looking at is from pi over 2 to pi. So let's use 2 pi over 3. This is negative. This is positive, or this is negative. This one's positive, so this region is positive. So this is the location of increasing. So between pi halves and pi. So my intervals of increasing is negative pi halves to 0, union between pi halves to pi, and decreasing on the interval between negative pi halves, union with 0 to pi halves. So I could now, if I wanted to, if I was asked to, I could draw the graph of this function. So here is negative pi halves, 0 of course, pi, halves, and then pi. So we know cosine is going to range between -1 and 1 because it's cosine squared. That means it's going to go between 1 and 0, between 0 and 1. Now we know that at pi we had a max or a min, one of the two. We just know it's a turning point. At negative pi halves, we had a turning point, and then like this. We know that we are decreasing in this interval, then increasing, then decreasing, and then increasing. So here's kind of a sketch of the graph based on the intervals of increasing and decreasing and using critical points. So that's kind of nice. So this will allow us to do a better sketching of our graphs by looking at the intervals of increasing and decreasing and looking at our critical points. Let's look at my next function that we're going to do the derivative. So f prime of x, this is going to be 2x, the square root of x plus 5, plus x squared multiplied by 1/2, multiplied by 1 over x plus 5 raised to the 1/2. Now I'm going to set this thing equal to 0, and I'm going to solve. So when I do that, I'm going to have 2x. And then because of the fact that this is in the denominator, and I want to make this the same common denominator to be able to figure out what is going to be important. So I'm going to set this thing equal to 0, and I'm going to multiply everything by the square root of x plus 5. When I do that, I'm going to get x plus 5, and then I'm going to have x squared multiplied by 2, or 1/2. Oh, so I better multiply by not just the square root, but also by the 2. So I'm going to have 4x, x plus 5 plus x squared. So what I did here is I multiplied everything by the 2 and the square root of x plus 5 raised to the 1/2. So that allowed me to clear this fraction, the fraction which had a 2 and the square root of x plus 5. When I multiplied this term by 2 and this square root, the square roots canceled each other out. So we have 4x because I had 2, that makes me 4, x plus 5. Then this gives me 4x squared plus 20x plus x squared is equal to 0. So I have 5x squared plus 20x is equal to 0. I'm going to factor out a 5 and an x, leaving me an x plus 4 is equal to 0. So when x is equal to 0 and when x is equal to -4. Now, the domain of this original function, so this is kind of important to think about because this didn't give me an interval. We have to talk about where the domain of this is defined. So we know this is going to be defined everywhere, the x squared part, but this factor, which is the square root of x plus 5, that part is going to dominate. So the domain of this function f of x is going to be from -5 to infinity. So 0 and -4 are within that domain, so those would be my critical points. Now, let's go back to, I kind of just sidestepped part of this, and I didn't worry too much about the, simplification before I jumped right into finding my critical points. So let's now go back to the simplification. So I have f prime of x. This is going to be equal to 2x, the square root of x plus 5, plus x squared over to the square root of x plus 5. This is going to be equal to 4x, x plus 5, plus x squared over to the square root of x plus 5. So this is going to give me 5x, x plus 4, all over to the square root of x plus 5. Okay, so now when I do this sign chart, I have the 5 and the 2, and I can ignore those because they're both positive. And when I do the sign chart, unlike my previous one in which I had a coefficient that was negative and I had to deal with that, this will not have the negative here, so I don't have to worry about it. So when I do my sign chart, like I learned in pre-calculus 1, I would have had x plus 4, and the square root of x plus 5. Those are the factors that I need to worry about. Now the intervals in which I have to break this apart is the first interval is between -5 and -4 because I have x is equal to -4 as a critical point. The next interval is between -4 and 0, and that's because I have a critical point at, I use that in red, I have a critical point at x is equal to 0. And then the other interval I have is from 0 to infinity. So now I have to choose something in this interval, so I'm going to use -4.5. -4.5 will make this negative, and this will always be positive because the square root has to be positive. So I'm just going to put positive all the way across those rows. This gives me a positive, so we know we are increasing on that interval. Let's choose something in here. Let's choose x is equal to -3. This is negative, this is positive, this is negative, so we are decreasing. And then let's just choose something over here. Let's just choose x is equal to 1. Positive, 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 increasing. So our intervals of increasing and decreasing, so increasing for this is between, I'm not going to worry about the endpoint of -5, so -5 to -4, union between 0 and infinity, and decreasing in the interval between -4 and 0. So if I were to sketch this graph, -5 is the lowest point I can have, and so when I put in -5, I'm going to get 0 out. When I look at my intervals, so between -5 and -4, I am increasing. So I'm increasing from -5 to -4, and then I decrease, so I'm probably going to have a turning point right there. And at 0, well, if I put 0 into the function, 0 will come out. So, and in that interval, I am decreasing. And then from 0 to infinity, I'm going up. So I'm going to have some graph that looks something like this based on my intervals of increasing, decreasing, and my critical points. Don't forget labeling your axes. Okay, let's take a look at my next example here. We're going to take the derivative of this. Now, we have to pay attention to the fact that we are looking at the absolute value of x. What does this do? Well, the absolute value of x is, we know that the domain of the original function cannot have negative numbers, like the natural log of x. So if I say that g of x is equal to the natural log of x, the domain of g of x has to be from 0 to infinity. But because we are allowing the absolute value of it, then my domain of f of x is going to be between -infinity and 0, union between 0 to infinity. So what I'm going to do is I'm going to consider this f of x as a piecewise function. So I'm going to take the left piece. When the natural log of -x, I'm going to consider this -x when x is less than 0, and the natural log of x when x is greater than 0. And that way, when x is negative, right, I can do the double negative, which will make it positive. And so that way allow me to do the derivative because I have the absolute value, and we've never learned how to do the derivative of an absolute value. So I'm going to do first when x is less than 0. F prime of x is going to be equal to -1 over x. Actually, it's going to be x. It's going to be 1 over x, and it's going to be a -1 over x times its derivative, which is -1. So it's just going to be 1 over x. Then f prime of x when x is greater than 0 is just going to be 1 over x multiplied by 1, which is 1 over x. So the only thing we have to worry about is when x is 0. So let's go ahead and do the sign chart. So 1 over x is my derivative. And the only thing I have to worry about is x is equal to 0 because that's where it's undefined. So I have the interval from negative infinity to 0 non-inclusive and from 0 to infinity. Let's choose x is equal to negative 2. This is negative. This means this is decreasing. This is positive. This means this is increasing. So the interval of decreasing is negative infinity to 0. Interval is 0 to infinity. There is no critical point, right? There's just no critical point. So if I were to sketch this graph, it's going to look something, here's y and here's x. We have a vertical asymptote at x is equal to 0. It's increasing on the interval from negative infinity to 0, and then it's going to approach the asymptote, so it's going to look something like that. And then it's increasing from 0 to infinity, so it's going to look something like that. Now we know that at 1 and at negative 1, because that's where the natural log crosses the x-axis, those locations would be there. So that's approximately what the graph would kind of look like. Okay, now let's go on to the next example here. So again, what I'm going to do is I'm going to do its derivative, f prime of x, so I can find critical point. So I have 2x minus 2 multiplied by 1 over x. So this time I'm going to clean this up algebraically before I jump in and find the critical point. So I'm going to make this a single common denominator. So I'll have 2x squared minus 2 all over x. So I set this thing equal to 0, and the only thing that is going to come into play is the numerator, because if I were to multiply both sides by x, the denominator is not part of the conversation. So when x, if I factor out a 2, so I have x squared minus 1 is equal to 0. So I have x minus 1, x plus 1 is equal to 0. So my critical points are at negative 1 and 1. Now, let's go to where this domain is defined. Well, x squared is totally fine, right? But the natural log of x is the part that is not defined everywhere. So the domain for this function, the domain of f of x, is from 0 to infinity. So even though I came up with a value, this negative 1 is not even part of the original domain, so I don't have to worry about that. So all I really have to worry about is at 1. So I have 2x, actually what I'm going to do is I'm going to ignore the 2 because it's positive, so I don't have to worry about that. But my factors are x minus 1, x plus 1, and x. So these are my 3 factors from here after it's been factored. And the only thing I have to worry about is when x is equal to 1. So I have the interval between 0 and 1, and the interval from 1 to infinity. I'm going to choose 0.5 when x is equal to 0.5. This will be negative, positive, positive, interval's negative, so we're decreasing. And I'm going to choose something on the right side of 1, so let's choose 2. Positive, 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 positive region, so increasing. So I know between at 1, I'm going decreasing and increasing. And if I were to sketch the graph, I'd probably want to put in 1 into the original function. When I put 1 into the original function, 1 comes out. It's y and here's x. So here is 1 and 1 comes out. So decreasing, increasing. So it's going to look something like that. Not drawn to scale, but it's a nice little sketch. Okay, now, critical points do not always correspond to local extrema, right? We've talked about that before. When we have a critical point, we could have a horizontal slide. So every time we have a critical point, doesn't mean that we are going to be changing from increasing to decreasing. It could just be continuously increasing. So it could just be a horizontal slide. This one is equal to 0, and it goes from decreasing to increasing. This one is not defined, so we don't worry about that. This is going from decreasing to decreasing. It has a critical point, but there's no extrema right there. And right here says no extrema. That brings us into the first derivative test. And that's kind of like what I was doing before with the sign chart. Suppose f is a continuous function over some interval I containing a critical point c. If f is differentiable over I except for possibly at the point c, and f of c satisfies one of these descriptions. If the sign changes from positive to negative, then it's a maxima. It could be local. Could be absolute, but it is going to be a maxima. If the sign changes from negative to positive, then it's a minima. It could be local, it could be absolute. If it has no sign change, then it is neither a local, it's not a extrema, it is a horizontal slide. So it is neither max nor min, local or absolute. So the first thing we want to do if we are using our first derivative test, which is what we just said, is we're going to find all the critical points. We're going to do a sign chart, and we're going to identify those locations of increasing and decreasing, and then we can identify what's happening at those critical points, whether or not it is a max or min, and then determine whether or not it's local or absolute. So the local and absolute stuff is not anything different than what we did in previous videos, but now we can say, oh, I know without plugging it in, I know for certain that this is a absolute, or this is a local max or min, or it's just a horizontal slide. So the first thing we want to do is find our critical points. So f prime of x is equal to negative 2x minus 1. We then set this equal to 0. So negative 2x minus 1 is equal to 0. So when x is equal to negative 1/2, I have a critical point. So I'm going to do a sign chart. I have negative 2x minus 1. It's the only thing I have to worry about. And when x is equal to negative 1/2. So I'm going to choose something on the left side. So in this interval, so I have this interval, I'm going to choose from negative infinity to negative 1/2. I'm going to choose x is equal to negative 1. So if I put in negative 1, this is positive, so this is increasing. Choose something on the other side of negative 1/2, so between negative 1/2 and infinity, this interval I'm going to choose x is equal to 0. When I put in 0, I'm going to get negative, so this is decreasing. So what we know is that on this interval, when x is equal to negative 1/2, we know the location based on going from increasing to decreasing, that this is a max. So we have a max at x is equal to negative 1/2. Now we don't know if it's an absolute or not until we look at our interval. So at negative 4, if I put a negative 4 and I'm going from negative 4 to negative 1/2, I'm increasing, we know that negative 4 is not going to be a max. And at 4, if I'm going at negative 1/2 and I'm going to 4 and I'm decreasing in that interval, we know that 4 is not going to produce a max either. So we know that the absolute max happens at x is equal to negative 1/2. And it is, well, I'm going to put in f of negative 1/2. And that's going to tell me whatever that value is. So if I put negative 1/2 into the original function, that's going to tell me what my max is. I know the location. So then I have to decide which one of these is going to give me the lowest value, because I need to find my absolute minima. One will be absolute, one will be local, but we don't use the endpoints as local. So I do f of 4, and I would do f of negative 4, and that would tell me which one of those two is going to be the minima. So I'm going to put those in my calculator. I'm going to put it into the original function, and remember the original function is negative, so it'll be negative 4 squared minus x, minus x, so this is minus 4, and then it is plus 2. And at the same time, I'm going to do negative 4, the quantity squared, minus a negative 4 plus 2. So this is going to be negative 16 minus 4 plus 2, and this one is going to be negative 16 plus 4 plus 2. So we can see when x is equal to 4, so at x is equal to 4, we have an absolute min, this is a min of negative 18. Okay, let's take a look at our next example. So for this example, we're going to again find our critical points. That's our first thing we're going to do. So we do f prime of x. This is going to give me 6x squared plus 6x minus 12. So I'm going to go ahead and set this equal to 0 and factor. So I'm going to factor out a 6 and have x squared plus x minus 2 is equal to 0. This becomes x plus 2, x minus 1. So I get x is equal to negative 2 and positive 1. Okay, this critical point of negative 2 is the end of the interval. So I don't have to really worry about that, other than the fact that I would plug it in to decide whether or not it's a min or a max. So when I do my chart here, I'm going to have my factors. I'm not going to worry about 6 again because 6 is positive. So my chart are the factors, which is x plus 2 and x minus 1. And I really only have to worry about between negative 2 and 1. So when x is equal to 1 is my critical point, and between 1 and 4. So I'm going to choose something in here. So I'm going to choose 0. This is positive, this is negative, so this is negative. So we are decreasing on this interval. I'm going to choose something in this interval. So I'm going to choose 2. This is positive, this is positive, this is positive. So this is increasing. So we know because I'm going decreasing to increasing, we know at x is equal to negative 1, we have a min. We don't know if it's the absolute or not, so we have a min. So now I have to plug in f of negative 2 into the original function and f of 4 into the original function, and that will tell me whether or not that at x is equal to 1, if that minimum is absolute or if it's just a local. And when I put in negative 2, I end up with 21 out. And when I put in 4, I end up with 129 out. So that tells me on this interval at x equals 1, I have a absolute. So if I put in 1, it is negative 6. So I have an absolute, so I should say absolute min of negative 6. And this tells me I have an absolute max of 129 at x is equal to 4. Because remember, when we talk about max and mins, they are the location and what they are not ordered pairs. Okay, let's take a look at the next example. So for this, we're going to go ahead and do the derivative. So we have f prime of x is equal to, and I'm going to use the chain rule. I'm going to rewrite this as x squared minus 1. Actually, you know what? Nah, I'll use the product rule. I almost never use a product rule, but since I have to clean this up anyways, I might as well use a product rule. So this is going to be 2x multiplied by the denominator, and minus the denominator's derivative, which is 2x multiplied by the numerator, all divided by the denominator squared. So this is going to give me 2x to the third minus 2x minus 2x to the third all over x squared minus 1, the quantity squared. So what we have is just 2x in the numerator and x squared minus 1 in the denominator. This tells me my only critical point is when x is equal to 0. And this should be negative 2x. All right, so the domain of this original function, domain of f, is everything except for negative 1 and 1. So x cannot equal negative 1 and 1. And the reason that is because this would be undefined. So because it's undefined at negative 1 and 1, and those values are in this interval, that tells me at negative 1 and 1, I must have vertical asymptotes. So I have vertical asymptotes at x is equal to negative 1 and at x is equal to positive 1. Well, what does that mean? Well, if I have vertical asymptotes, that tells me that my function is going either all the way up to infinity or all the way down to negative infinity. Well, these combined tell me I have no absolute extrema on that interval, because I'm either going all the way up to infinity or I'm going all the way down to negative infinity. So there is no absolute extremas in there. So I don't have to worry about checking the endpoints. All I have to figure out is what's happening with the critical point. So my factors are the negative 2x, x minus 1, the quantity squared, and x plus 1, the quantity squared. And I only have to look at when x is equal to 0. Now you're thinking, how did these get squared? Well, if I factor this x plus 1 and x minus 1, it'd be x plus 1 squared, x minus 1 squared, so they're both squared over here. So the interval I'm looking at is between -1 and 0, and between 0 and 1, because that's the location of the horizontal or the vertical asymptotes. So I'm going to choose, say, x is equal to -0.5. So this will be positive. These will be positive regardless of what happens. And then I'm going to choose x is equal to 0.5, and this is going to be negative. So I'm increasing, and then I'm decreasing. So I'm increasing, decreasing. So that tells us that we have, and remember we have no absolutes, that tells me that I have a local max at x is equal to 0. I put 0 into the original function, and I'm going to get 0 out. So the local max at x equals 0 is 0. And that's it for that one. Now, let's take a look at this function. So let's do its derivative, f prime of x. The derivative of the inverse tangent is 1 over 1 plus x squared, and then derivative of 3 of x squared, or x cubed, is going to be 3x squared. Making a common denominator, I'm going to get 1 minus 3x squared, 1 plus x squared, all over 1 plus x squared. Now, this from negative tangent inverse of x, there's no place in which it's undefined, because x cubed is defined everywhere and tangent inverse is defined everywhere on the negative infinity to infinity. And then, so we look at this. Okay, so what do we have here? Well, this is equal to, this is going to be equal to 1 minus 3x squared minus 3x to the 4th, all over 1 plus x squared. So let's rearrange this and pull out a negative. So I have 3x to the 4th plus 3x squared minus 1, all over 1 plus x squared. Okay, so again, the numerator is the only thing that we have to worry about, so we're going to set that equal to 0. So I have negative 3x to the 4th, I pulled that negative out, plus 3x squared minus 1 is equal to 0. So I can't factor this, so I'm going to have to throw in the quadratic, and it's going to be x squared is going to be equal to, because it's not x, it's x squared, is going to be equal to negative b, so negative 3, plus or minus the square root of b squared, which is going to be 9, minus 4, a is 3, c is negative 1, all over 2 times that 3. Oh, this is not going to be a nice number. Okay, we can ignore the negative. So the reason we can ignore the negative is because x is equal to, so it's x squared is equal to, so when I do this, I'm not going to worry about the negative part, so I only have the positive to worry about. So it'll be negative 3 plus, and then underneath the square root, I'm going to get 9 plus 12, which is 21 over 6. And for that, I'm going to need a calculator. And so I've got x squared I have as 0.2638. I'm going to take the square root of that because I want x. So x is equal to 0.5135. But remember, since I took the square root of both sides, there'll be a positive and a negative. So that tells me I have critical points of x is equal to negative 0.5135 and x is equal to 0.5135. Now, it is unlikely I'm going to be able to do a nice little sign chart. So what I have to do is I have to choose something between -1 and -0.5. So I would choose f prime of, say, -0.6. And I would do f prime of 0. I would do f prime of 0.6, so 0.6. And the reason I would do this rather than my sign chart is because this isn't going to factor nicely. So I put in -0.6 and I get a negative number. I put in 0, I get a positive number. And these aren't actual answers, so let me put arrows here. and then I put in 0.6 and I get a negative number. And I'm putting these values into my derivative, okay? So this tells me between -1, so between -1 and negative 0.5135, we are negative. So that means we are decreasing. So I'm decreasing. And then the other location I am decreasing. So I chose these numbers that were between my critical points. I chose these numbers because they were between my critical points. So the other location I am decreasing is from 0.5135 to 1. And I am increasing in the interval between negative 0.5135 and 0.5135. So those are the locations or the intervals of increasing and decreasing. Okay, so I would put in -1 and 1 into my original function. So we know that at negative 0.5, because I'm going on the right side of 0.5, I am decreasing and then I'm increasing. We know that this is a min, and then on 0.5, I'm coming in increasing and leave decreasing. We know this is a max. We don't know if these are absolutes, so what I'd have to do is I'd have to go back to the original function and put in -1. I'd have to put in 1. I'd have to put in negative 0.5135, and then I'd have to put in positive 0.5135, and then I'd be able to determine which ones were the maxes and which ones were the mins. And as it turns out, when I put in 1 and -1, they are going to still be less than what I do when I put in my 0.513 and my negative 0.513. So my max is, my negative is actually going to give me a min. So my min, my absolute min at x is equal to negative 0.1535 is negative 0.339, and then my absolute max at x is equal to the positive 0.5135 is 0.339. So I found the locations of my max and mins and my absolutes in this case, and they happened at the critical point. Okay, 4.1 guarantees the existence of absolute values on only closed intervals. Can that be said about absolute extrema on intervals that are not closed? Think about that one and we can discuss it in class. The next thing we're going to look at is concavity and inflection points. And I know this is a long video because there's a lot that's covering in this video. There's a lot of things that are happening. So, concavity and inflection points. Oh, look at this example. I kind of skipped over this. Let's do this one in class. What I want you to do is think about how do we deal with when x is in the exponent. Remember, this is just a hint. What you're going to do is you're going to say y is equal to x raised to the x, and then you're going to say the natural log of y is equal to x raised, the natural log of x, or x times the natural log of x, using the rules of the laws of logs, and then do that derivative. But let's do that one in class. Okay. So we haven't talked about this before, but now we're going to talk about this. We're going to talk about concavity and inflection points. So what we look at is it a cup or a spill? So a cup is concave up. So here's a concave up, and if it's a spill, it's a concave down. So what we do is we are going to look at the derivatives. So let f, and let's look at our first definition. Let f be a function differentiable on an open interval I. If f prime is increasing on I, then we say f is concave up over I. If f prime is decreasing, then we say it is concave down over I. So if my derivative is increasing, we are concave up. And if my derivative is decreasing, we are concave down. So how do we test for concavity? Well, what we do is we take the second derivative. So this is our test for concavity. We're going to take the second derivative and we're going to determine where the second derivative is greater than 0 or less than 0. If the second derivative is greater than 0, then it's concave up. If the second derivative is less than 0, then it is concave down. So let's look at some graphs that help us understand this a little bit better. So my first graph here is I've done my derivative, my first derivative. My second derivative I set equal to 0, and then my second derivative set equal to 0. This is the point of inflection in which I'm going to change concavity. On this side of the graph, my second derivative, see how this second derivative would have been a negative value. Even though the first derivative would have been positive, my second derivative would have been negative because I'm concave down. I'm increasing, but I'm concave down. Now right here, this point of inflection will also probably be likely because I am kind of have a horizontal slide there. It's probably a critical point too. So you can have a point of inflection and a critical point be the same thing. Now in this interval, I'm still increasing, so I'm increasing this entire time. So I have a critical point right here at C. I'm increasing this entire time. I have a horizontal slide at C. It is my point of inflection. My second derivative would all have been positive in this region because it is concave up. Now, for this one, this looks like it may be a squared function, a quadratic function. I have a critical point, and I also have a, looks like it could be an inflection point. Well, let's look to see what happens if I start out with f prime. So f of x, let's call this x squared. And let's assume that it's moved over, so it'd be minus 4x plus 4. Here's a quadratic that has been moved over that would satisfy this. F prime of x is going to give me 2x minus 4. And then f double prime of x is just going to give me 2. Oh. Well, then I don't really have a point of inflection because I can't set that thing equal to 0. Now, I am concave up this entire region because this derivative on the entire interval would be positive because it's a positive 2. Here's another example. This looks like it may be the cube root that's been moved over. Now, we have concave up, we have concave down. F prime double prime of C does not exist. So the inflection point it changes in it. We have a inflection point. This is probably the location of the critical point. Now the reason f double prime and f prime probably does not exist is because it is a vertical tangent. Lastly, we have one that's a corner, and we have concave down, concave down. This is not an inflection point because it does not exist, and it also does not change concavity at that point. So f is continuous at A, f changes concavity at A, then we say that A comma f of A is an inflection point of f. So let's sketch the graph with this information. We are continuous from negative infinity to infinity. The first derivative is less than 0 between negative infinity and 0. What does that tell me? That tells me I am going down, I am decreasing. The second derivative is greater than 0, so that tells me I am concave up. On the interval between 0 to infinity, my first derivative is positive. That means I am increasing. And it also tells me my second derivative is greater than 0, so I'm also concave up. So bringing this information together, notice how when I read through there, I kind of drew the shape. So I'm concave up. So right there at 0, I'm concave up, and I'm going from decreasing to increasing. So that's a sketch of the graph. Could look like something else, but it looks like that as an example. Now what about this one? F prime of x is less than 0, so that tells me I am decreasing, so I am decreasing. And then also f prime double prime of x is greater than 0, so not only am I decreasing, but I am concave up from negative infinity to 0. F double prime of f of x is positive, so I am increasing. But my derivative here, my second derivative, is less than 0, so I have something that looks like that. So my graph might look something like this, y and x. So I am decreasing, so I might have something that looks like that. I'm decreasing. And then I have concavity is going to be concave down, but I'm decreasing, or I'm increasing. So maybe this graph is going to be undefined at 0, so it's going to look something like that. So maybe it's a piecewise graph. For this example, we're going to determine the intervals in which we are concave down or concave up and identify any points of inflection. Okay, so the first thing I'm going to do is the first derivative. So I have 12x cubed minus 12x squared minus 12x plus 12. I'm going to do my second derivative, and my second derivative is 36x squared minus 24x minus 12. I'm going to set my second derivative equal to 0 and solve. These will give me my points of inflection if they are actual true points of inflection. So I'm going to factor out a 12. So I have 12. 3x squared minus 2x minus 1 is equal to 0. So divide both sides by 12 and factor, and I have 3x and x minus 1, x plus 1 is equal to 0. And so I have x is equal to negative 1/3 and x is equal to 1. Now, these are possible points of inflection. So what I'm going to do is I am going to do a sign chart of these factors. I don't have to worry about 12, because we talked about that. 12 is positive, so I don't have to worry about that. I'm going to have 3x plus 1. I'm going to have x minus 1. And the points of inflection tells me that x at negative 1/3 and x at 1. X is equal to 1. My interval is from negative infinity to negative 1/3, from negative 1/3 to 1, and then 1 to infinity. So I'm going to choose something in this interval. I'm going to choose, say, negative 1. I put in negative 1. This is negative, negative. This is positive. So this tells me I'm concave up. I'm going to choose something in this region. Let's choose 0. So positive, negative, negative. So I'm concave down. Let's choose something in this region. Let's choose 2. Positive, 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 concave up. So we actually do have points of inflection. The x values are negative 1/3 and x. So as ordered pairs, because points of inflection are points, I would do f of the negative 1/3, and I'd put that into my original function, and I would also do f of 1 into my original function. And then I would answer this as ordered pairs. When I put in negative 1/3, I got 0.5. We'll do 0.52. So my point of inflection is negative 1/3 and 0.51. And then my other point of inflection, I put in 1. And I'm going to have 3 minus 4 minus 6 plus 12 plus 1. And I get 6 out. So I have 1, 6. So these are my points of inflection. These are my 2 points of inflection. Now, I could then do my first derivative and figure out where my critical points are, and then sketch the graph from there. Okay. Here, we're asked to find the concavity, concave up or concave down, and any points of inflection. Oh, this is a long video. I apologize. This is such a long video. So let's go ahead and do the first derivative f prime of x in here, since I'm going to rewrite this as 1 plus x squared raised to the negative 1. This is negative 1 plus x squared raised to the negative 2 multiplied by 2x. So then my second derivative of x, so that's going to be, oh, that'd be a positive. Excuse me, that'd be a positive too. I moved it down so it'd be positive. So this is going to be 2x over 1 plus x squared, and it's a negative. So my second derivative is going to be so much fun. So I'm going to have negative 2x, the derivative of negative 2x, which is just 2, and then multiplied by the denominator, 1 plus x squared, minus negative 2x multiplied by the derivative of the denominator, which is 2, 1 plus x squared, raised to the 1, multiplied by 2x, all over 1 plus x squared, now raised to the 4th power. And when that's all cleaned up, I'm going to get 2, 3x squared minus 1, all over x squared plus 1 raised to the 3rd power. Okay, so numerator is the only thing I care about. So when x is equal to, let me see, this is going to be negative square root of 1 over 3 and the positive square root of 1 over 3. So those are the two locations. Now here's the thing. It is unlikely I'm going to do, well, yeah, it's already kind of great. It's already kind of factored. So let's do the sign chart. So the 2 I don't have to worry about. So this is going to be x, and it's going to be plus the square root of 1/3, x minus the square root of 1/3, and then x squared plus 1, the quantity cubed. So I'm going to have when x is equal to negative square root of 1/3, when x is equal to the positive square root of 1/3. First interval is not with that. The first interval is from negative infinity to negative square root of 1/3. This is from negative square root of 1/3 to square root of 1/3. And then the last one is square root of 1/3 to infinity. So I'm going to choose something on the left. I'm going to choose negative 1. So I have negative 1. This will be negative. This will be negative. And this will be positive because I take that negative 1 and square it. So it'll be positive, so this region is positive. I'm going to choose something in between, so I'm going to choose 0. So positive, negative, positive. So this is negative. Choose something on the other side. Let's choose 1. So positive, positive, and positive, positive, positive. So this region is positive. So that tells me when x, my points of inflection, and I do have points of inflection happen at negative square root of 1/3, at square root of 1/3. So this tells me I'm concave up, concave down, and concave up. And then actually to find the points, I would put those back into the original function and figure out what those points are. That was a whole lot of not fun. Let's take a look at B. Now with B, this probably is a whole lot of not fun again. So we have g prime of x is going to be the derivative, so it's going to be 1/3 multiplied by 1 over x minus 4 raised to the negative 2/3. So then the second derivative, g double prime of x, I don't know what that's doing there. I don't know why I did that weirdness. So g double prime of x is going to be equal to 1/3 multiplied by a negative 2/3 multiplied by 1 over x minus 4 raised to the negative 5/3. Now, we're not going to get a critical point because it won't be defined at, we know something's happening at x is equal to 4. Why do we know something's happening at x equals to 4? Well, this is a cube root that has just been moved over to positive 4, 0 is the location in which it has the vertical tangent. So we know that this has a vertical tangent, but I'm not going to get a critical point because it's not going to be defined. But that doesn't mean that, or I'm not going to get a point of inflection because it's not defined there. But that doesn't mean I'm not changing from concave up to concave down. We know at x is equal to 4, we have a vertical tangent, which means it's not defined for the first or the second derivative right there. But that doesn't mean that we don't have concavity changes. So how do we determine that? Well, we're going to have to go to the second derivative here. And I'm going to have to choose something on the left side of 4. So maybe I'm going to do f double prime of, say, negative, let's put in 0. I always like 0 if we can. and f double prime of something on the right of 4. So let's choose 5 because that won't be too bad. And when I choose those two numbers, I'm going to have, when I put in 0, I'm going to get a positive number. So I'm going to get positive. When I put in 5, I'm going to get negative. So I wasn't actually able to do a sign chart. So the sign chart that I have been doing up in most of the time doesn't always work because what's happening is it's not defined for that point of inflection. Even though we're changing from concave up to concave down, I can't actually put in 4 because it's not defined at 4. But I do have a place in which it's changing from negative and from positive to negative in terms of concavity. Now let's take a look at C. So f prime of x is going to be 1 over 1 plus x squared. Okay. Now tangent inverse also has a shape kind of like the cube root. It kind of looks like this, except for the difference between the cube root and the f tangent inverse is that it's going to approach, as x gets really large, it's going to approach the line y is equal to pi over 2. And as x get really small, it's going to approach the line y is equal to negative pi over 2. So it's going to look something like that. So if I were to do the second derivative, which isn't too bad, the second derivative, f double prime, if I write this as 1 plus x squared raised to the negative 1, this is going to be negative 1 over 1 plus x squared raised to the 2 power multiplied by 2x. So at x is equal to 0, we're going to get a point of inflection. So right here we get this point of inflection, which it is actually defined. So I guess we don't have a vertical tangent there. So we have when x is equal to 0, and I would be able to put that into a sign chart and determine what's happening. Now let's look at our last one here. D h prime of t is equal to negative sine of t. H double prime of t is going to be equal to negative cosine of t. I don't know what's happening in my pen. H prime of t is going to be negative cosine of t. So in this interval between negative pi to pi, negative cosine of t happens when t is equal to negative pi over 2 and pi over 2. So we can do a sign chart for this one. It's just negative cosine of t. That's my second derivative. And I have negative pi over 2, and I have pi over 2. I'm going to put in something on the left side. So let's put in x is equal to negative 2 pi over 3, negative 2 pi over 3, negative. Let's put in something in between. Let's put in 0. So when I put in 0, when I put in negative pi over 2, because it's a negative cosine, this is positive, so concave up. Put in 0, it's negative, so concave down. Put in pi over 2, it's positive, so concave up. When x is equal to 2 pi over 3, because I can't put in pi over 2. And so I know those are my concavity. So my points of inflection happen when x is equal to negative pi over 2, and pi over 2. So to actually find the point, I would do h of negative pi over 2 to get a y value, and I would do h of pi over 2 to get the y value, because these are actually ordered pairs. These are the places, these are locations, these are ordered pairs. Okay, second derivative test, which says, hey, I don't have to necessarily do a sign chart, because the second derivative test says I can do the first derivative, and then I can do the second derivative. If I put my critical point in the second derivative, and it's greater than 0, it's a minimum. If I put my critical point in my second derivative and it's negative, it is a max. And if it's 0, it is inconclusive. So let's take a look at a couple of these examples. Locate the points of the critical points and then use the second derivative test to determine if they're maxes or mins. So I'm going to do first my first derivative. So g prime of x is going to be equal to 3x squared. G double prime of x is going to be equal to 6x. My critical point is at x is equal to 0. That is the location for x. However, when I put it in here, when I put 0 in there, it is inconclusive. Well, what does that mean for me? Well, that means I have a critical point, but that doesn't mean it's a max or min. And how would I decide that? Well, then I'd have to go back to a regular sign chart. So I have 3x squared. Notice I go for my regular sign chart. When my second derivative test is inconclusive, I'm going to go to my sign chart. X is equal to 0. Choose something on the left-hand side in the interval from negative infinity to 0. I'm going to choose x is equal to negative 1, positive, positive. So we are increasing from 0 to infinity. X is equal to 1, positive and positive. So we're increasing. So this tells me that at 0, what's happening is I have a critical point, but it is neither a max or a min. Let's take a look at B. So P prime of x. I'm going to do the derivative of the numerator, which is 1, x squared plus 20. I'm going to do minus, it'll be minus. I'm going to do the product or quotient rule, x minus 1, or x minus 4, excuse me. Derivative of the denominator is just going to be 2x all over x squared plus 20, the quantity squared. So this is going to be x squared plus 20 minus 2x plus 8x minus 2x squared plus 8x all over x squared plus 20, the quantity squared. So this is going to give me negative x squared plus 8x plus 20 all over x squared plus 20, the quantity squared. Well, that's a whole lot of fun. My critical points first, so it only comes from the numerator. So my critical points, I'm going to factor out a negative, giving me x squared minus 8x minus 20 is equal to 0. This factors into x minus 10, x plus 2 is equal to 0. So my critical points happen at 10 and negative 2. Now, I am probably disinclined to do the second derivative because it's not going to be a lot of fun, but let's go ahead and do the second derivative. So f double prime of x is equal to the derivative of the numerator, which is going to be negative 2x plus 8, multiplied by the denominator, which is going to be x squared plus 20, the quantity squared, minus the derivative of the denominator, which is 2x squared plus 20 multiplied by 2x multiplied by the numerator, which was negative x squared plus 8x plus 20, all over my denominator, which was x squared plus 20, raised now to the 4th power. Now, see, that's just not nice. That is just not nice. So I don't think I'd probably do that. I don't think I would use the second derivative test because it's way too much work. Since I already have this thing factored, right, I would probably just go down here and do the sign chart. So I would have, in the numerator, I'd have a negative 1, because I have to pay attention to that negative 1, x minus 10, x plus 2, and x squared plus 20, the quantity squared. And then I would just do a sign chart to decide instead of the second derivative test. When x is equal to negative 2, when x is equal to 10. So this is the interval from negative infinity to negative 2, negative 2 to 10, and then 10 to infinity. Oh, notice I put that negative 1, so I need to put a negative 1 down here. Boom. Okay, so I would probably do it that way. So I would put in, say, x is equal to negative 3. This is negative, this is negative, this is positive, this is negative, this is negative. So I'm decreasing in that region. I would put in x is equal to 0. So I have, when I put in 0, I'm going to have negative, positive, positive, negative. So this is positive, so we're increasing. So this is an extrema. I don't know if it's absolute or not. And then I'd put in, say, x is equal to 11, positive, 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 negative. So it's negative, so it's going down. So this tells me that that is an extrema. This is a max, the other one's a min, and I don't know if it's the absolutes or not. Okay, let's take a look at C. Hopefully C is nice. So the first derivative, g prime of x, is going to be 4x cubed over 2 minus 24x. That's not too bad. Let's go ahead and factor that to find critical points. This 2 and that 4 were canceled down into a 2. So what I really have, I'll factor out a 2x, leaving me x squared minus 12. So my critical points is x is equal to 0 and plus and minus the square root of 12. Let's do our second derivative, g double prime of x. This is just going to be 236x squared minus 24. So then now I can put in 0, right? So g double prime of 0, this isn't too bad to put in. This is negative 24. Because it's a negative, if you remember, all the way up here it says, wait, if that thing is negative, then it must be a max. So we have a max at x is equal to 0. Okay. G double prime of the square root of 12. When I put in the square root of 12 and I square it, it's going to be much bigger. So 12 times 6 is going to be much bigger than 24. So this will be positive. So this is a min at x is equal to the square root of 12. And the same thing is going to happen when I put in the negative square root because it's going to be positive. So g double prime of negative square root of 12 is also going to be positive. So I have a min at x is equal to negative square root of 12. And I didn't have to do a sign chart on that one. So that was kind of nice. Let's take a look at h. So h prime of x is equal to x minus, that's going to be 4, x plus a raised to the third power. My critical point is x is equal to a. H double prime of x is going to be 12, x plus a squared. So if I put something on the left side of a, so whatever a is, doesn't matter what a is. If I put something on the left side of a, because I'm going to be squaring it, right? It's going to be positive. So if I have left side of a, x plus a, the quantity squared, is greater than 0. If I have something on the right side of a, then I'm going to have still x plus a, the quantity squared, is going to be greater than 0. What does this tell me? Well, a, because I'm positive on both sides, right? On the left side of a and the right side of a. So what this is telling me, that's probably a horizontal slide, and it should be negative a. And it should be the left side of negative a and the right side of negative a. So here's the thing. That isn't the second derivative test. The second derivative test, if I were to put in negative a, is going to be inconclusive. So what does this mean? Well, this means because the second derivative test is inconclusive, and I know that I'm going to have something on the left and right side of negative a is going to be positive because it's going to be squared, then I know that I have a horizontal slide there, which means that critical point does not produce a minimum or a maximum. Okay. Holy crap, this keeps going. Will this ever end? Oh no, it's forever. Oh dear Lord. Oh, if you guys are feeling it, I'm feeling it. Oh, okay. Let's power on through. Okay. So we're trying to decide which one of these graphs belong to the original function, which one of these graphs belong to the first derivative, and which one of these graphs belong to the second derivative. So let's start with A. With A, I have a max. So if we assume A is the original function, I better be crossing on my derivative. Here, I have a min, better be crossing on my derivative here. I have a max, I better be crossing on my derivative here. Min, better be crossing. Max, better be crossing. Min, I better be crossing. Okay, so that doesn't line up. So we know that A cannot be the original function because I don't have anything consistently crossing. It looks like B might be crossing, but if I look right at here, right? The problem here is if I think that a is the original function and b is the derivative, then in particular right here, I should have a crossing. So I know that can't be the original function. Okay, so let's assume b is the original function. So if b is the original function right here, I better have a derivative. That looks okay. B, that looks okay. B, that looks okay. B, oh, that's kind of a problem. So I don't think b is my original function. So let's see C if it's my original function. So C is my original function. Here's a max, here's a crossing. C is my original here's a, excuse me, that was a min and a crossing. So a max and a crossing, a min and a crossing. Right here, everything's crossing. A max and a crossing. Oh, so I think C is F. And I think B is F prime because that seems to be matching. Now I'm going to look to see if wherever B has max, if A is crossing. B has a max here, A is crossing. B has a min here, A is crossing. B has a max here. Let me see, B is the dashed line. B has a max here, A is crossing. It's not what I want to look at. If B has a max here, A is crossing. Everything's going on right here. B has a min, A is crossing. I think I said that wrong. Min, crossing, everything's crossing. So I think A is the second derivative based on max and mins and crossing of the x-axis. Okay, here's something that we did in our pre-calculus 1 class. In our pre-calculus 1 class, we did carrying capacity. We did logarithmic functions in which we had a place in which we can no longer grow any larger. And we actually have formulas for that. This is like when you have fish in a pond and you will have an initial amount of growth in that pond will be pretty big and it'll be increasing. And it'll be increasing at a large positive rate. And then we're going to get this point of inflection. And then when we get this point of inflection, we're still going to be increasing, but the rate of increase starts to slow down. So the population of the fish in this pond starts to slow down until I get to the carrying capacity of the pond and I can't have any more fish in the pond. So we've seen these logistic growth models. One of the ways that we can describe populations of fish in a pond, infection rates, right? Because at some point we will have hit all the infections that are going to happen, whether it is the infection of a town or a village or just a household. Eventually you will hit as most you can infect, right? So if you have a household of 5 people, at most you can infect 5 people with a cold, common cold or something. So this is an example in which we can see that the growth rate is increasing the entire time, but the rate in which I'm increasing starts to slow down. I'm increasing quickly in terms of infections or the number of fish in the pond, and I'm still increasing in the number of fish in the pond, but it's not increasing as much. So here's a nice recap of derivative properties. I'm not going to go through this because they're all right here. They're in your book. Happy to go over that, but here's that. Here's some guidelines. So I would consider pausing this and reading through it and or making notes. They're in the book as well, OpenStax. So read through all of those. These are ways to go through it. Now, there is a lot of these, right? And this is a long video and we're getting bored, right? We're all kind of getting bored. And so what we're going to do, there's a whole bunch. There's a whole bunch going on here. Let's just go through one of them and go through its entirety of sketching the graph. So we've done square roots, we've done some rational functions, we've done polynomials. Now I'm going to do one of these polynomials because, you know, this is a long video and plenty of opportunity to go through these at a later date. I'm going to go ahead and do B. So the way you would approach any of these polynomials are going to be the same. If you were sketching the graph, right, so we know the domain of this original function is negative infinity to infinity. I would find my x-intercepts if it's not too difficult. So I would set my derivative or my original function equal to 0. So, and I'd factor out, in this case, I'm going to factor out a 2x to the 4th. And when I factor out a 2x to the 4th, I'm going to get x squared minus 3 over 2 is equal to 0. And the reason I'm doing this is because I'm trying to find my x-intercepts. So when x is equal to 0 and when x is equal to the plus and minus the square root of 3 over 2. So those are the locations of my x-intercepts. Now, I'd also find my y-intercept when x is 0, my y-intercept. So my x-intercepts are at 0, 0, at the negative square root of 3 over 2, comma 0, and the square root of 3 over 2, comma 0. So those are my x-intercepts. I'd also talk about the behavior of the graph. My leading coefficient is 2. My power is 6, so my a sub n is greater than 0. My degree is positive. It's positive. So these two combined tell me that my behavior as x goes to negative infinity, my function goes up. And as x goes to positive infinity, my function also goes up. Okay. So now I've got some information. I know at 0, I know, it's not going to be drawn to scale, the square root of 3 over 2, negative, comma 0, and the square root of 3 over 2, comma 0 are my x-intercepts. I know my behavior is here. I know my behavior is here. I know at my x-intercepts, this is all this stuff all this stuff I'm talking about is pre-calculus 1. The multiplicity of all of these, at this multiplicity, because it does a power of 4, is going to bounce. So we know that whatever's happening there is going to bounce. So we bounce there, we touch and bounce off, and these are passes because their multiplicity is 1. So I know it's going to look something like this. And that's something we know without doing any calculus. This is all pre-calculus 1. Now, let's do the calculus part. All of this stuff is in pre-calculus. Do your OpenStax pre-calculus chapter 3. So let's do the derivatives so we can figure out the points of inflection, and we can look at our max and min areas, right? So we can actually find this stuff now. So f prime of x, and this is going to be 12x to the 5th minus 12x to the 3rd. I'm going to set this thing equal to 0 and solve. So I'm going to factor out a 12x to the 3rd, leaving me x squared minus 1. So my critical points happen at negative 1 and 1. So right here at negative 1 and right here at positive 1, I'm going to get max and mins. I'm going to have, well, these are critical points, I should say, and also at 0. Well, we kind of knew that. Okay, so now I'm going to do my second derivative, f double prime of x. My second derivative is going to be 60x to the 4th minus 36x squared. So if I put in 0, right, if I put in 0, because I'm going to do the second derivative test, I put in 0, it's not going to tell me anything. But if I put in negative 1, this is going to be a positive number. And if I put in 1, this is going to be a positive number. So this confirms that these are the locations of the mins. And that's kind of what we graphed. You know, we kind of graphed that. Now, if I want to know how far I'm actually going to go down, so I can find the location, I can actually find the minimums. I'm going to do f of 1. I'm going to put 1 in the original function, and it's going to be 2 minus 3, which is negative 1. So this location, I'm going to go negative 1, negative 1. I'm going to put in negative 1. Actually, that should have been negative 1, so I'm going to put in a positive 1. And it's still going to be negative 1. So this is also going to be at 1 comma negative 1. So I now have those parts, right? So this stuff is calculus. Before, that was all pre-calculus. Now, I'm also going to set my second derivative equal to 0 and find my points of inflection. So I'm going to factor out, let me see, 12x squared. So I'm going to factor out a 12x squared, leaving me 5x squared minus 3 is equal to 0. So at x is equal to 0 and plus and minus the square root of 3/5. So these are going to be my points of inflection. So I'm going to have a point of inflection right here and a point of inflection right there. Now, if I go and do a sign chart for the second derivative, I'm going to find in this region that I am concave down. I'm going to find in this region I'm concave up. And if I actually want to know this actual location, I would do f of negative square root of 3/5. I'm going to do f of square root of 3/5. And then it'll tell me the actual y value besides just the x value location. And so now I have a much better sketch of my graph using, beyond my pre-calculus skills, my calculus skills. Okay, so let me see, which one do I want to do next? Which one do I want to do next? Let's look at C. So C is interesting. We're going to do the same thing with C. So I'm going to do g prime of x. Now, I have to talk about the domain of g. Domain of g is from 0 to infinity because of this piece. So g prime of x is going to be 2x natural log of x, and then it's going to be plus x squared multiplied by 1 over x. So this is going to be 2x, the natural log of x plus x. I'm going to factor out an x, leaving me 2, the natural log of x plus 1. So the reason I'm doing this is to find my critical points. Now, I can't use pre-calculus 1 skills because we didn't learn how to graph x squared, the natural log of x. We learned how to graph polynomials and rational functions. So my critical points are x is equal to 0, but that's not part of my domain, so that's actually not going to be a critical point. So then I'm going to put 2, the natural log of x plus 1 is equal to 0. So the natural log of x is equal to negative 1/2. So I'm going to do e to both sides. So I have x is equal to e raised to the negative 1/2. Okay, so that is my critical point. My critical point is e raised to the negative 1/2. What I'm going to do now is I'm going to do my second derivative. Okay, so I'm going to do my second derivative. G double prime of x is going to be 2, the natural log of x, plus 2x multiplied by 1 over x, and then plus 1. So this is going to be 2, the natural log of x, plus 2 plus 1. So 2, the natural log of x plus 3. Okay, so I'm going to set this thing equal to 0 so I can find my point of inflection, if it is a point of inflection. And so I'm going to have, let me see, the natural log of x is equal to 3/2. E, the natural log of x, is equal to e raised to the negative 3/2. That should be negative 3/2. So x is equal to e raised to the negative 3/2. So this is a possible point of inflection. Happens at x is equal to e raised to the negative 3/2. Okay, so now what? Well, so I found a critical point, and I found a possible point of inflection, and we don't know what's going on with any of those. So what I can do is, let's do a sign. Well, let's put this value into my second derivative and see whether or not it's positive or negative, so I can determine, hopefully, whether or not this is going to do anything. So I'm going to put it in right here. So f double prime of e raised to the negative 1/2 is equal to 2, the natural log of e raised to the negative 1/2 plus 3. So natural log of e raised to the negative 1/2 is negative 1/2 times 2, so it's negative 1 plus 3. So this is greater than 0. So this is a minima. So we know that we have a minima right here. All right, now The point of inflection, well, it's a possible point of inflection. I'll need to know what's going on either side. So I'm going to take the second derivative here and do a sign chart. And the only thing I have to worry about is e raised to the negative 3/2. And I have 2 the natural log of x plus 3. Now we knew what happens when we said x is equal to e raised to the negative 1/2. And that's actually on the other side. So e raised to the negative 1/2. We put that in there and we knew right here, right? We did that already. We know that this is positive, so we are concave up in that region. And so we'll choose something on the other side, maybe e, let me see, what would be a number smaller than that? Let's choose e raised to the negative 5/3. I think that should do it. Let me see. Five-thirds, yeah, negative 5/3 is smaller than that, so e raised to the negative 5/3, 5/3. So I put 5/3 in there, and so I'm going to get 2 times 5 because of the rules of logs. It's negative 5/3. I'm going to get a negative 10/3, so this is going to be negative, so that means I'm concave down. Okay, so I have that actually is a point of inflection, and I would find the location of it by putting in e raised to the negative 3/2 back into the original function, and from there I would find all the points. So what does this graph look like? Plugging everything into my calculator. First of all, we know we can't put in 0, so we're going to get close to 0, but we're not going to get 0 as an input or even for an output. Right, so it's going to be undefined there. Now, this is not going to be drawn to scale. We know at x is equal to e raised to the negative 3/2. That's going to, and if I were to put that in, I'm going to get approximately a negative 0.069. So right here at this point, my point of inflection is e raised to negative 3/2, and I put it in the original function, and I get like a negative 0.069 each out, something like that. So I know in this region I am concave down. I know when I hit e raised to the negative 1/2, e raised to the negative 1/2, I have a minimum, and I'm concave up from this point on. And so I'm going to have something that looks like that. That's what my graph is going to look like approximately, not drawn to scale. And if I wanted to know where this thing crosses the x-axis, I would set this thing equal to 0 and solve. And that would happen to be when x is equal to 1, because when x is equal to 1, the natural log of 1 is 0. So right here at x is equal to 1. So that would be my location. I don't have any y-intercepts. I have an x-intercept. And that's pretty much it. So I'm going to stop here because this is a long enough video. If you want to go over any of these examples in class, let's go over them in class. Otherwise, there's a lot of videos out there to watch on curve sketching from beginning to end. I would make sure that you know how to do it from beginning to end with a polynomial and then maybe with a log. The rational functions are interesting, but they're long, and this is a long enough video as it is. So that's it. That's enough. I'll talk to you in class.